I hope you can see my screen.
Yes, ma'am.
Okay. So, good afternoon, all. Today, I'm going to conduct a session for Introductory Organic Chemistry Second NPTEL course. The course instructors are Professor Haniraj Chakrapani and Professor Neeraja Dashaputre, and I'm your PMRF teaching assistant Simran. As we have learned in the later lecture that about the NMR spectroscopy, so I'm continuing it with another session. So the topic of this session is NMR. So I hope you guys got the solutions for the previous assignment and you got the answers as well. So if you have any problem about that questions or answers, just let me know so that we can proceed for the today's lecture. So you have some problems or not? Am I audible?
Yes, ma'am.
Okay, so there is no problems, right? So
Yeah, ma'am. No problem, ma'am.
okay, so I'm continuing with today's lecture. Okay, so I'm starting with problem one. So it is based on the concept which we have learned earlier. So the problem one consists which of the hydrogens from A to D in the following molecules give a triplet signal in a normal 1H NMR spectrum. So if you have gone through to my previous lecture, I have told you about a n plus 1 multiplicity rule, right? For the hydrogen, that is actually what the 2n plus 1 rule, right? But for the hydrogen, as we are considering that this I value is half. That is why we are considering that it is a n plus 1 rule instead of 2 and I plus 1. Okay, this is 2 and I plus 1, but for hydrogen I value is half, so we are considering that it is an n plus 1 rule. So they are asking in the question that how many like which proton is going to give you a triplet. So, as we know that particular in this particular case, let me remove it so that you can get a higher idea. Okay. So, starting with this methyl group, okay, just we have to calculate the multiplicity. So, as we know that these protons have no neighboring hydrogen to get a multiplicity or to get a splitting pattern, right? So, for this proton, we have to get a singlet, right? Because there is no nearby hydrogen which will split this signal into further signals. So we are going to get a singlet for this particular methyl group as we have discussed previously. So there is no confusion about it, right? Okay.
Ma'am, actually, this is my first class, ma'am.
Okay. This is your first class. All right.
Yes, ma'am. Okay, ma'am.
Okay. So I have to tell you all the things. Okay.
Okay, ma'am. Thank you, ma'am.
Okay. So this is your first class. So I'm telling you that this is methyl, right? And we have hydrogens here. Okay.
Okay, ma'am.
Hydrogens. So, as we know, as just tell me that you have gone through my previous lecture video or not.
Not, ma'am.
Okay, so that I can know now that how much knowledge you have or how much concept you have for this. So first of all, have to know that for the multiplicity pattern, we consider a particular formula, that is the n plus one rule, right?
Okay, ma'am.
Yeah. So this is particularly 2ni plus 1, but we cut short it into n plus 1 rule because for the hydrogens, the I value, that is the spin number, which is half for the hydrogens, right? So that is why we are telling that 2ni is not the rule, it is the n plus 1 rule. Because if you write this, see, See, this value is high, and this is n is the number of hydrogens which are present in the vicinity. Okay. So for this formula, if we consider that this I is half, just tell me that if it is half, right? And this is 2n plus 1. Okay. So if you cut this, then what is the formula which you now have got? This is n plus 1, right? Have you got it?
Okay, ma'am.
Yeah. So for hydrogens, the spin moment is half. So for that, I'm not going to repeat all the things. I'm just going to give you the gist. Just go to my videos and you will get to know that what I'm speaking about. Okay.
Okay,
So,
ma'am. Sure, ma'am.
अरे, charger दे रहा. Okay. So, just coming to the question, now for this methyl, as you can see that there is no hydrogen which is present in the vicinity, right, of this carbon. See, this is the methyl group, but there is no hydrogens here to split this signal into further signals. In the NMR, you will get a singlet for this proton, but if you have adjacent proton on this carbon, you will get a further splitting for this pattern. You are not going to see a singlet then. You are going to see a further multi-splitted pattern. Okay. Is this clear?
Yes, ma'am.
Okay. So see, this is the methyl group that is giving you singlet. Now coming to this carbonyl. There is no hydrogen which is attached to this carbonyl, right? So these are not going to give you any signal in this 1H NMR. Now coming to this CH2. This is in the vicinity of this particular hydrogen. Okay. If you see a CH2 signal, that is a 1 signal in the 1H NMR. Okay. Now, this signal is further splitted by this hydrogen which is present in the vicinity of this particular hydrogen, that is CH2. These are the equivalent protons. So, this is the hydrogen now due to which the splitting is caused in this particular CH2 signal in the NMR. Now, this is one hydrogen, okay, which is going to split this singlet into further. So this is one hydrogen. So according to this rule, that is n plus 1, which we have concluded, n is our 1. Okay. N is the number of hydrogen which is present in the vicinity of the particular hydrogen which we are talking about. So if it is 1, then 1 plus 1 is equals to 2. Then you are going to get a doublet for this CH2. Now this singlet in 1H NMR will split into a doublet pattern. Into a doublet pattern. So you are going to see this pattern in 1H NMR instead of a singlet for this CH2. Is it clear? Just tell me if it is clear to you.
Okay.
Sorry.
Okay, ma'am. Okay, ma'am.
Okay. So if it is clear, then coming to this CH, coming to this CH. Now you have
Okay.
this hydrogens, right? This H2 hydrogens in the vicinity of this CH and this oxygen. But oxygen, as you know, is not going to give you a 1H NMR signal, right? And these methyls are far away because of this oxygen which is connected in between this CH and methyl group. These methyl group will not interact in this signal splitting because of the long range coupling. It will not interact with this coupling. Now you are going to give, or you are going to see a signal which is splitted by this CH2 group, not by this methyl group. Okay, because of long range coupling. Now for this CH group, if this number of hydrogen for H2 is what? 2, then according to n plus 1 rule, if the number of hydrogens are 2, then 2 plus 1 is going to give you a 3. That is a triplet signal. So now you are seeing for the CH, this one signal is splitted into a triplet because of this CH2. Okay, not because of methyl, because methyl are far away from this CH, because of the oxygen which is present in between this CH and methyl group. Okay, so you are going to give C a triplet for this CH, and for these methyl, again the things are same. Because of the oxygen which is present between this CH and the methyl group, the methyl will not feel a splitting pattern because of CH. Okay, and also other carbons are very far away to show the splitting pattern for this hydrogen. Okay, so now you are going to see a singlet again for these particular methyl groups. These two methyl groups, you are going to see a singlet. So, what was the question? The question was that which of the hydrogens from A to D are going to give a triplet signal in 1H NMR spectrum. So, as we have concluded that this methyl is going to give you a singlet, this CH2 is going to give you a what? Doublet. Okay, because of this CH proton. And this CH is going to give you a triplet because of this two hydrogens which are present in the vicinity of this CH group. Okay, and now these two methyl groups again will give you a singlet because CH is very far away because of the oxygen which is present in between this CH and methyl to show the splitting. So the correct answer will be what? Just tell me what is the correct answer of amongst these A, B, C, D. Which is the proton which is going to give you a triplet?
CH2 proton, ma'am, I think so.
C proton, right? Hydrogen C will going to give you a triplet. Is it clear, right?
Yes, ma'am.
Yeah, you got the right answer. So hydrogen A, B, and D will not going to give you a triplet because they are showing you a singlet and doublet in the 1H NMR. Okay, if it is clear, I'm moving to the problem number 2. I hope these solutions are clear to you. So the
Yeah,
problem,
ma'am.
yeah. So the problem number 2 is the number of peaks possible in proton NMR for the following compound is. So question is asking what are the number of peaks that are possible for the proton NMR of this compound. So first we have to look at the protons which are present in this particular system. So this is H, this is again H, this is H, and this is H. Okay. So these are the hydrogens which are present in this system. No hydrogen otherwise, right? These are the four which are present only. So they are asking that number of peaks that are possible in proton NMR. So we first have to signify that these are the hydrogens. Are they equivalent or non-equivalent? So how we are going to get that thing? See, the number of peaks is like number of hydrogens that are present, different type of hydrogen that are present in the system. If you have only one kind of hydrogens, yeah, protons in the system, you are going to get a single peak in the 1H NMR. If you have more than one hydrogen, like one set of hydrogen that are chemically equivalent, so for that first you have to know that these protons all are the sp2 hybridized, right? All have having same environment. How? That this hydrogen, the oxygen is present in the vicinity. For this hydrogen, oxygen is also present in the vicinity. It is coming for that oxygen and hydrogen environment. Again, this proton, oxygen, hydrogen environment. For this proton, oxygen and hydrogen, oxygen and hydrogen that are present in this system. Okay, so these protons having all the environment that are same. See, this Ha, if I suggested Ha, this Ha proton is in the vicinity of this oxygen and this hydrogen. Okay, now coming to this Hb proton, if we say this Hb, then this Hb proton is in the vicinity of this hydrogen Ha and oxygen. If I said about this Hc proton, then again the similar thing happens, that it is a sp2 hybridized or hydrogen, as well as this oxygen and hydrogen are present in the vicinity of this Hc. If we talk about this Hd, again oxygen and hydrogen is the only species that is coming adjacent to this Hd proton. So the chemical shift value, which we are going to look at in the further slides. So chemical shift value for these protons Ha, B, C, and D all are the same because the environment of Ha, Hb, Hc, and Hd are same. Are you getting my point that if a proton have a same chemical environment, it was possessed to have a same chemical shift, it will resonate at a same resonance frequency. So you have to look at the system first, how many set of protons are present in a particular system for the number of peaks we are going to assign. See what happens here, that if two set of protons are different, that if we talk about some other molecule like this, if we talk about a toluene, okay, toluene is nothing but benzene ring with a methyl group. So if we talk about this toluene, so how many signal you are going to get? See, these are all the sp2 hybridized hydrogens. Okay, I'm not mentioning the hydrogens here, but you have to see that these are the hydrogens. So all the sp2 hybridized hydrogen, but these hydrogen that are present here is in vicinity of this methyl and hydrogens. Methyl and hydrogens for this as well. So these two are chemically equivalent hydrogens, but for this hydrogen, can you suggest this? No. Because for this hydrogens, one hydrogen again here is the environment which they are facing. But for this also, so these are the two chemically equivalent protons, and these two are the again similar protons. So now the signal which we are going to get for these four proton is different, because here for these two protons the methyl environment and hydrogen environment is there. So these are the Ha protons, Ha, and these are the Hb protons, because Hb protons are surrounded by hydrogens only, but Ha protons are surrounded by methyl and one hydrogen. So similar with this case, here it is the symmetrical molecule that all the hydrogens having the same environment. So the number of possible peaks for in the proton NMR would be, just tell me from these options like 2, 3, 1, and 4, how many signals are this molecule is going to give you? Any suggestions? Any guesses?
Sorry, ma'am, I didn't know the correct answer.
No, no, it's okay if you don't know the answer. I'm not asking about the answer. You just have to make a guess. According to the understanding which I have just talked about now, just tell me the guess what you think, that this molecule is symmetrical. So these Ha, Hb, Hc, and Hd, all the protons have same environment. Like oxygen and hydrogen are the vicinity of these particular hydrogens. So how many signal should they give? Just make a guess. I'm not asking about the answer.
Okay, ma'am, I will try. I think one, ma'am. Only one
Yeah,
signal.
yeah, very good. This is the correct answer. That is the C, because the hydrogens are equivalent in this particular case because the molecule is symmetrical. See, if you don't have this oxygen here, okay, just
Okay,
suppose
ma'am.
that this oxygen is not here. Now, this Ha and Hd proton will be chemically distinguished by this Hb and Hc proton, because now there is a carbon here and again a hydrogen here. Okay. So now you are not going to get a single signal for the proton NMR. Now you will get a signal for Ha and Hd, 1. For Hb and Hc, you will get a signal, 2, right? And for these hydrogens also you will going to get a signal if it is ch2. Okay, but
Okay, ma'am.
in this case it is symmetrical, so you are going to get a one NMR signal in the proton NMR. So you are not going to get a signal like 2, not 3, and not 4. So the correct option is C. I hope you guys understood this, and in the later slides we will get to know how different molecules have different environment. Okay, So this classes basically depends on the number of possible protons and the effect which I want to suggest. This like chemical shift values, you are going to focus on this only for this session. So coming to the problem 3. So this is like more the shielding effect, what would be the larger? So the option A is lower the chemical shift, B is no change in the chemical shift, C is higher the chemical shift, D is more the peak splitting. See, more the shielding effect. I have talked about this in the previous slide. In the previous lecture, I have talked about this. That one sec, I think someone wants to join. Okay. Okay, so in the previous lecture I have talked about the shielding effect. See what is the shielding effect? As you have not attended the class, then I will let you know again that if you have a nucleus, right? If you talked about a proton, if it is surrounded by a electron density, okay, on the carbon, then the and if you are applying a magnetic field in this direction, okay, then the surrounding electron density which the nucleus is having is produce a small induced magnetic field that will be opposite in the direction of the applied magnetic field. So the induced magnetic field that is going to generate because of the electron density that is present in the around the nucleus, which is opposite in the direction of the applied magnetic field, due to which now the nucleus is not going to feel the proper applied magnetic field which you have applied. Now, the applied magnetic field which our nucleus is going to feel is B, that is the magnetic field, that is the applied magnetic field, and minus applied magnetic field minus the induced magnetic field which is induced by the electron density which is surrounding the nucleus. Okay. So now if we have a greater electron density around the nucleus, the value of this shielding magnetic field, that is the shielding induced magnetic field, will increase. Now the nucleus is not going to uh, experience the applied magnetic field which the we have applied, right? Now it would be minus by the induced magnetic field which is generated by the electron density around the nucleus, due to which it affects the local magnetic field that nucleus experience. It feels the frequency at which the nucleus resonates. It changes the frequency at which particular nucleus resonates, because now it is not feeling the particular applied magnetic field which you have applied. Now it is feeling the magnetic field is equals to applied magnetic field minus the induced magnetic field that is generated by the electron density around the nucleus. Okay, so now it is not that it is the shielded nucleus, so it is going to frequency at a low frequency. It is going to resonate at a low frequency. So this is the value, that is the chemical shift value by which we can address that how much resonance frequency a particular nucleus is feeling. Okay, I think someone is there. Please try to join on time. It is very hectic if the lecture is going on. It is very hectic to join anyone. Okay. So where was I? So this is what the shielding effect is. So if a nucleus is shielded by the electron density which is surrounding it, okay. So now it will resonate at the low frequency. It will resonate early. Okay. Low frequency means that now it will have a a field value of the chemical shift. A field value. A field value means that the value will be less for the chemical shift. See, in this case, if the electron density we are going to increase, right? Then this carbon, then these hydrogens will resonate at a low resonance frequency than the applied magnetic field. So if you are applying a magnetic field in this direction and you have a nucleus here, so the electron density which is surrounding the nucleus will induce a small magnetic field which is the opposite magnetic field which is applied in the direction of applied magnetic field. So now the magnetic field which our nucleus is feeling is not as much as the applied magnetic field. It is feeling the magnetic field which is minus by the shielding of the induced magnetic field. Okay, so now it will resonate at a lower frequency. It will change the frequency. Basically, the shielding will change the frequency at which the nucleus is resonating in the 1H NMR. If the shielding is high for a particular nucleus, then the frequency at which it will resonate will be lower. Okay. And if the shielding is less, like if this value of shielding is very much low than the applied magnetic field, then the nucleus will be facing a downfield shift. That is the de-shielded shift. Okay, so I hope it is clear. Actually, these concepts I have already talked about in the previous lecture. So if someone is attending the first lecture this, then it is very difficult to cope up with these words. So I prefer you, after seeing this lecture, please go to my previous videos which I have uploaded on YouTube and just have a look on that. Okay. So for this particular question, if we have a more shielding effect, that is, if we have more electron density which is surrounding at a particular nucleus, now it is more. Now the applied magnetic field which our nucleus is going to feel is very low because the shielding effect is very high. So the our nucleus will resonate at a lower frequency than the usual proton do. So, coming to the statement that each proton in a molecule is shielded from the applied magnetic field to an extent that depends on the electron density surrounding it. Okay, the greater the electron density around the nucleus, greater the induced counter field that opposes the applied magnetic field. That is, which is how I have explained that the greater the electron density around the nucleus, more the secondary induced magnetic field is going to generate, and which will be opposing your applied magnetic field now. So the counter field that shields a nucleus diminishes the net applied magnetic field that nucleus is going to experience. Now it is not experiencing the net applied magnetic field which you have applied. Now it will be shielded. So it will be the applied magnetic field minus the magnetic field which is generating from the secondary induced magnetic orbital. Okay, so as a result, the nucleus will be going to process at a lower frequency. So if the shielding effect is low, right? If the shielding effect is low, then our nucleus is going to process at a higher frequency, that is at higher chemical shift value. This means that more the shielding effect, lower is the chemical shift value. Okay, lower is the frequency at which it particularly resonates in the 1H NMR. Okay, is it clear?
Ma'am, if you don't mind, please once again repeat, ma'am.
Okay, okay,
If okay.
okay. So, see, I'm repeating from the starting. Okay. So, the question first, you have to understand the question. See, more the shielding effect. If the shielding effect is more, which will be going to change? Lower it the chemical shift value, no change in the chemical shift value, higher the chemical shift value, and more the peak splitting. Okay, these are the particular option which we have to figure out. So, the shielding effect, as I have discussed, if you have a proton, right, and around the proton you have electron density, high electron density. Okay, now these electron density is resonating under the applied magnetic field. If you have applied a magnetic field in the direction of proton, then the electron density which is surrounding this proton will induce a further magnetic field that is present in the opposite direction of this applied magnetic field. So now if someone is opposing this applied magnetic field, so now the electron density of this nucleus is opposing the applied magnetic field. You have applied something, and on the counter side is there is something which is opposing. Okay, so now you are not going to feel as much hindrance or as much field effect that is applied by the particular person or the thing. Now you are going to feel what? you are going to feel the applied magnetic field minus the shielding effect which is causing due to the electron density which is surrounding the nucleus. Is it clear? Is this thing clear?
Yes, ma'am.
Okay. If this thing is clear, see what happens here. If something is obstructing you from going there, okay. Now you are not feeling that much applied magnetic field. You are feeling the applied magnetic field minus the magnetic field which is generating it by the electron density which is surrounding a nucleus. Okay. So if this is the condition, higher the shielding, that is why what I am said that like higher the shielding. Why is shielding is there? Because of the electron density. So higher the electron density which is surrounding the nucleus, higher will be the shielding effect. And if the shielding effect is very much higher than the applied magnetic field, then nucleus is not going to feel anything. Like nucleus is not going to feel anything. So it will be resonate at a lower frequency. If you apply a low frequency, okay, then only it will resonate in the 1H NMR. It will going to show up in the 1H NMR. If you apply like little bit of applied magnetic field, then only it will resonate at this particular frequency. So if this shielding effect is low, now applied magnetic field is very high, then in that case the shielding is low. Now the nucleus is facing all the magnetic field that is applied by you. Okay, so now it is very difficult for the nucleus to resonate. So now you have to increase the resonance frequency, the field, and you then the nucleus will be showing up in the 1H NMR only then. Okay, but if you have a high shielding, then the nucleus will show up very early in the 1H NMR. If you give certain frequency, then it will resonate at this particular frequency. So the shielding effect is lowering the frequency at which the particular nucleus is resonating in 1H NMR. Is it clear now?
Okay, ma'am.
Okay, so what happens here now? You first have to look at my video too. Then you will get to know, you will get a certain idea about this particular thing. Okay, it is not
Sure, ma'am.
straightforward. I know that it is not very straightforward to understand at a very first class, but you will get to understand it, particularly seeing the video which I have uploaded. Okay. So, coming to the question now, more the shielding effect, then what will happen? So, the shielding effect is high, that is, the electron density at the particular nucleus is high. So, the electron density is high, then it will shield the applied magnetic field more. So, now the our nucleus is going to resonate at a lower frequency. If you are providing a certain frequency, it will show up in 1H NMR. So, now if the resonance frequency is low, then lower the chemical shift value. Then our chemical shift value, because chemical shift value is nothing na, it is a variation in frequency which is the chemical shift value. So the frequency at which our nucleus is resonating has a direct significance with the chemical shift. So if the resonance frequency is lowering, then the chemical shift value is also lowering for that particular nucleus. Okay, so the correct option will be A, not the B. There is no change in chemical shift. How would it not be changed? Because if the shielding effect is high, then the chemical shift will be low. And if the shielding effect is low, then the chemical shift will be high. So this is a current scenario which we are dealing about. So higher the chemical shift, no. The peak splitting is nothing to do with the shielding effect. Okay. So I hope this solution is clear to all of you. So I am proceeding with problem 4 now. So the problem 4 is how many number of peaks are possible in 1H NMR spectra of following compound. So this is the compound. I have just done the expansion of this to get a better knowledge of you. See guys, what happens here is this is the ethyl chloride. So one of the carbon having 3 hydrogens and one of the carbon having the 2 hydrogens. Now these 3 hydrogen as of the methyl hydrogens. So they are asking about the number of peaks, not the splitting. Okay. So number of peaks is depending on the number of hydrogen that are present in our system. Number of different hydrogen, chemically different hydrogen, number of different hydrogens. Okay. So number of chemically different hydrogen. Chemically different matlab like having the different environment in the 1H NMR. Okay, having the different environment. So talking about these methyl hydrogens. Now these methyl hydrogen have CH2 protons in the vicinity. Okay, so they all are having a same environment, that these are the equivalent protons. Are you agree with me that these hydrogens are equivalent because they having the same environment? They are connected to a carbon. They are connected to a carbon, and then they are in the vicinity of hydrogens. So these methyl protons are the equivalent protons. So they are going to show up like a single signal in the 1H NMR. Okay, this thing is clear. Now these protons are equivalent, these three protons, because they have chemically same environment. Now coming to these methylene protons, that is the CH2 protons. Now these CH2 protons, these both are having the same environment because they are connected to carbon, and then they are in the vicinity of this chlorine. So how many signals you are supposed to get in the 1H NMR? Based on these, there is one. Okay. So now this ethyl chloride will show up like this. See, these methyl protons having the same chemical environment, so that is why they are showing up as a single signal in the 1H NMR. And these methylene protons, they are also having the same environment, like these are connected to this carbon as well as this chlorine. So that is why these are the another set of protons that are going to give you a signal in 1H NMR. So we have two kind of protons that are present in the system, which are going to give you two peaks in the 1H NMR. First peak is because of this methyl hydrogens, and second peak is because of the methylene hydrogens. Is it clear?
Yes, ma'am.
Yeah. Based on the chemical environment, you have to look at the number of chemically different hydrogens that are present in the system to answer these kind of questions. So the number of peaks are directly dependent on the number of chemically different hydrogens which are present in the system. So here there are two sort of proton, that is the methyl proton and again the methylene protons, that are having the different connectivity, like that are having a different environment in the 1H in the molecule. That is why they are going to show up as a 2 peak in 1H NMR. Okay, so the correct answer will be 2. Because of the methyl and methylene protons, you are going to get a single signal, one for this, one for this. So collectively, they will show you a 2 peaks in 1H NMR. Okay, so the correct option will be B, not the A, not C, not D. So correct option will be B. You are going to get two signals in the 1H NMR. One is because of the methyl protons and second is because of the methylene protons. So I hope it is clear. Now I'm going to forward for the problem 5. Now in the problem 5, they are asking that in NMR spectrum, the nuclei in a field resonate at. First option is high frequency, second is low frequency, C, it is constant throughout the spectrum, D, it doesn't depends on chemical shift. See what happens here is, first you have to look at the upfield. What is upfield? What is downfield? You have to look at. Now there is a scale, right? When you are going towards this low chemical shift value, then you are said to have a field shift or the shielded region. You know, I have talked about the shielding effect, right? So if you have the high shielding effect, then you have the low resonance frequency and the low chemical shift value. So now you can relate that if you are going towards a lower chemical shift value, then your proton is the shielded one, and you are going through a field situation. So now if you are going in the right hand side of the scale, delta ppm, that is the chemical shift scale in which we are calculating it. So if you are going towards the right, towards the left, sorry, then you are going to have a de-shielded proton and the downfield. So it is, just don't get confused about the upfield and downfield. You are going to say that the upfield is the downshield and downfield is the upshield. It's not like that. So just focus on this and you will get to know that if the shielding effect is there, just connect with that. If the shielding effect is there, then the nuclei is going to resonate at a low frequency. Low frequency meaning that it has a lower chemical shift. Lower chemical shift, then we are saying that the nuclei is upfield. It's shifted upfield. That is the lower chemical shift value that than the downshield effect. Now, if a nuclei has a lower shielding effect, then we have talked about that the applied magnetic field is the only field which is experiencing by the nucleus, and that is why it is going to get you a de-shielded region. Now the de-shielded region is the downfield region in the delta ppm scale. Okay, just please just remember this thing very carefully, because it is the important thing in the 1H NMR to predict which is the downfield proton, which is the upfield proton, which is the shielded region, or which is the de-shielded region. So on the left hand side of the delta ppm table you have the de-shielded region, and on the right hand side you have the shielded region. So now coming to the question, that in NMR spectrum the nuclei in upfield resonate at. Now if you have a nuclei, see, if you have a nuclei in this particular upfield region means that the lower frequency region or the de-shielded region, that is what, like if this nuclei is coming at this shielded region, this means that the electron density around this is very high, because if the electron density is high, only then uh, it will be generating a secondary magnetic field which is very high than the applied magnetic field. So that is why it is going to give you a shielded um, NMR or a shielded resonance frequency. Okay, now, if a nuclei is resonating at a upfield, then what is the particular thing which it will be feeling? Like high frequency, low frequency, it is constant throughout the spectrum. It is not very constant throughout the spectrum, because if a nuclei is experiencing a upfield resonate, that means that it is feeling a shielded region, then the nuclei will be having a lower chemical shift value, right? As we have talked about that here, coming to the delta ppm scale of the chemical shift, if a proton is coming at this shielded region, that means it have a high electron density, and due to which the secondary magnetic resonance is very high. That is why it is opposing towards the applied magnetic field. So the now the nucleus which would experiencing it is not the applied magnetic field, it is the applied magnetic field minus the secondary orbital generation, that is the magnetic field that is generated by the electron density around the nucleus, that is the secondary magnetic field. So applied magnetic field minus the secondary magnetic field is the magnetic field which is experiencing by the nucleus in the shielded case. Okay, so here when the nucleus is shielded, then the chemical shift value will be upfield. That is the lower chemical shift value the nuclei have. So the question is asking that if the nuclei has a upfield resonance, that the nucleus is resonating at a upfield in the NMR, then what is the particular thing it have? High frequency, low frequency, or it doesn't depend on chemical shift? Because as we have told that the chemical shift is directly related to the resonance frequency at which the nuclei is resonating, so it is not the case that it doesn't depends on chemical shift. Because if a nuclei is resonating at a high field, upfield, downfield, then it actually changes the chemical shift value of the nuclei. So we can't say that it doesn't depends on the chemical shift. So amongst these two options, now we have to figure it out that which is the correct option. Now in NMR spectrum, the nuclei in upfield resonate at. If the here a nuclei is there, and it is resonating at a up field value, then the chemical shift value is low. And I have talked about that if the chemical shift value is low, then the nuclei is resonating at a lower frequency. That if you give a low frequency to the nuclei, it will resonate at that frequency. Is it clear or not? Just tell me.
Clear, ma'am. This concept is clear.
Okay, if it is clear, because you have to just uh, you have to just figure this out. The question, right? This problem number 3 is same, is linked to the problem number 5. Here we are, there we are telling that if the shielding effect is high, then what will happen? If the shielding effect is high, then the nuclei is going towards a lower shift value because it is resonating at a lower resonance frequency. So now they are asking, if a nuclei is resonating at a upfield, that is, I have told you that this is the upfield region, which is the shielded region. So now if nuclei is resonating at this region, then it is surely having a low chemical shift. So if it is having a low chemical shift, then it is surely resonating at a low resonance frequency. If the nuclei is resonating in the de-shielded region, it is having a high resonance frequency. So you guys have to just keep this thing in mind, that about the resonance frequency or about the chemical shift, the relation between them. So you have to recall it so that you remember it for further. Okay. So for this, then if you got the thing, then what is the answer? What will be the answer between A and B for this question?
Low frequency, ma'am.
Low
B option.
frequency. Very good. So the answer will be the low frequency because our field region is lie at a low chemical shift value, and if the chemical shift value is low, that means that our nuclei is very much crowded by the electron density. So it is now resonating at a lower frequency. So correct option will be B. Okay. I hope you guys got the answer. Now I'm coming to the problem 6. So in the problem 6, they are asking that the possible number of peaks in one HNMR spectrum of the following structure is. So this is the structure. I have expanded this structure. So they are asking the number of peaks again. As we know that the number of peaks are directly related to the number of hydrogen that are chemically different in a particular compound. So here we are just have to think that how many number of chemically different protons are there in the system. If we figure out this, then we can surely tell that the how many number of peaks in one HNMR the compound is going to give. Okay, so coming to the structure, now here we have two kind of proton. One is this CH proton and one is this methylene protons. Now this hydrogen is surrounded by this carbon and two chlorine atoms, right? But in this case, these protons are surrounded by this carbon and one chlorine atom. So you tell me that these hydrogen, if we figure out this like three hydrogens, Ha, Hb, and Hc. If we say that these are the three hydrogens, so does they have the same chemical shift value or same environment? Does they have the same environment? A, B, C. You got my question? See what happens here, that this Ha proton is connected to this carbon, which in turn is connected to these two chlorine atoms. So now chlorine atoms have the electron withdrawing effect. So they have now they will abstract the protons from, sorry, for the electron density from here. So now this proton will be more downshield or the de-shielded region than this Hb and Hc. So we are not going to get into deep at that the de-shielded and shielded region. We are just figure it out that this Ha, Hb, and Hc, the chemical environment for these proton are same or not. Okay. So if we see about Ha, then it is attached to the carbon, which in turn attached to two chlorine atoms. So this proton is very much different from HbNHC, because in HbNHC there is only one chlorine atom which is present in the same carbon, that is the vicinity. Okay, so we are going to get how many signals for this particular compound? If anyone knows, just make a guess.
Ma'am, two peaks, ma'am, because CH proton and CH2 protons.
Yeah, very good. Two peaks are there because HA will resonate at different resonance frequency, but HB and HC, these protons are sorry, these protons are connected to carbon and chlorine only. So these are having the same environment. So that is why this HB and HC are the chemically equivalent proton. But HA is not chemically equivalent from the HB and HC point of view. So HA is going to give you one signal in the NHNMR separately, and HB and HC will going to give you one signal in the 1H together. So 1 plus 1 is equals to 2. So there are two peaks which you are going to see in 1H spectrum. So B would be the answer, that the two peaks are corresponding to this methylene group, and this CH proton is going to show up like a 2 signal in 1H NMR spectrum. So we are not talking about the multiplicity here, we are talking about the number of peaks. It is not that the splitting is not there, because here the H is present, HA is splitted by HB and HC. HB is splitted by HA and HC. Okay. So these are the things which you have to keep in mind, that spin multiplicity is also there, which we have talked about. But in this particular case, if you have asked the number of peaks in 1H NMR only, then you have to figure it out that how many type of protons, how many set of protons which are having different chemical shift environment is there in the compound. For the multiplicity, always remember the rule n plus 1 rule. Okay. So you will get the answer of every question if you apply these basic things on that. Okay, so the answer of this particular problem is 2. So the correct option will be B, that is 2. So if it is clear, then I'm going to problem 7. So now the problem 7 is, which of the following solvent is not used in NMR? See, what we not used in NMR is the type of solvent which itself is going to give you a sharp peak in NMR. NMR is about the 1H NMR, right? So the protons, generally we are not prefer the proton solvents in NMR. We use the deuterated solvents. Why deuterated? Because deuterium doesn't resonate at the same frequency at as that of 1H. So deuterium and hydrogen have very much different resonance frequency. That is why we are using the deuterated solvent, not the solvent which are containing protons, which itself is giving so much sharp signal that your compound signal is getting diminished over it, because you are using solvent is in excess. Okay, you are preparing a sample, you are keeping the compound low in quantity, but you are using excess solvent to resolve it. So what happens there is, if the solvent have if the solvent have its own proton, its own set of proton, then it will going to have a very sharp peak in the 1HNMR, because you have used an excess solvent in the compound. So the compound will peaks will get diminished. So what is the point of recording the NMR? You record NMR to justify, to purify, to check that you have obtained a purified product or not. You choose to check that you have obtained the correct product or not, right? So why, what is the need of NMR? Because to interpreting things, to purify things, right? So if you are using a protonated solvent, then how you are expecting that the compound signals are very high and your solvent is less? Because if you are preparing a sample, then you are using minimum amount of compound and high amount of solvent. Then if the solvent have itself in contributing peaks, then how the NMR will record the small peaks which your compound is going to give? So you will get a very sharp signal for solvent if you are using a protonated solvent for preparing the NMR sample. Is it clear? Is it clear, or I have to explain it again? Okay. Once again, okay. See what happens. Here the question is asking which is the solvent you are not going to use in NMR. You cannot use in NMR. Okay. So NMR is the NMR is the basically a thing which is used to characterize the compounds. If you are obtaining a compound in lab, okay, you are prepared a compound, then you are thinking that it is not the compound or the compound which you have like desired compound. It is not have. So for that, for confirming the particular compound you have obtained is the desired or not, you are going to perform set of experiments like NMR, IR, mass. You are going to go for every particular spectroscopy. Okay, to confirm that the compound you have obtained is the desired compound. So, if you are preparing a sample, then you are going to get small amount of compound in the NMR tube, because for recording the NMR you need only 20 to 20 mg of compound, right? So in the NMR tube, if you are going to put the 20 mg compound, but the solvent is like zero point 0.4 ml. You need zero point 0.4 ml to dissolve. Generally, I'm just talking about in the general. Okay, it is not the fixed rule that zero point 0.4 ml solvent will dissolve everything every time. It's not like that. It is the general rule which we are using for making an NMR sample. So you are going to get 20 mg compound dissolved in zero point 0.4 ml of solvent which we are using for recording the NMR. So the excess which is present in the excess, the compound or the solvent? Of course, the solvent. It is in the excess, right? So if your solvent itself has the peaks which can interact or which can give us signal in one HNMR, so what is so it will be very sharp because of the intensity, because of the concentration of the solvent. If it has some protons, then the signal which you are going to look at in NMR will be very high for that particular solvent. And your compound peaks, the compound of interest peaks, are very much diminished than that of the solvent. Okay, so you doesn't follow this particular practice, and you need that a deuterated solvent is used instead of the protonated solvent to record the NMR. Because in the case of deuterium, na, deuterium will resonate at a very different magnetic field than the hydrogens. It will not resonate at the magnetic field which is there for the hydrogens. It will resonate at the high magnetic field. So unless you are not providing that magnetic field to the deuterium, it is not going to show up in NMR. Okay, so in that case, you are not going to get a very sharp peak for solvent, right? You are not going to get any big sharp peak for solvent. Now your peaks for compound is also high as that of the solvent peak. So now the purpose of recording the NMR is accomplished, because now you can easily characterize the compound peaks. You are not just left out with the solvent peak in excess. Okay, is it clear? Okay. So, see, this is the explanation. So, what happens here is deuterated solvents are traditionally very expensive, but we then only we are using it in NMR. Because the deuterium is doesn't show up at the same resonance frequency or the same magnetic field as that of the proton. So the magnetic field at which it resonates is very much high than the proton. That is why in proton NMR deuterium will not give you a signal. That is why we are going for the deuterated solvents. Okay, to suppress the large solvent signal that would otherwise occur in the proton NMR spectrum. So mostly 1s spectrum are therefore recorded in the deuterated solvent, because it absorb at a completely different frequency. Okay, so now they are asking that which is the solvent which is not used in NMR. Is it the D2O, CHCl3, that is chloroform, CCl4, tetrachloromethane, CDCl3? So which is the solvent which is not used in NMR? So D2O, it is the water, deuterated water, right? This is the deuterated water. So if you're going to use the water as the for preparing the NMR sample. You will get the peak for the hydrogens that are present in water, and which is in excess. That is why you will get a very intense peak. So your compound peak will be very much lower in intensity than the solvent peak. That is why we are going to replace H2O with D2O. Okay. Now here in the chloroform. Here in chloroform you have a proton. Now, this proton will show up in the 1H NMR and will give you, if you are going to use it as solvent, now, it will give you a very intense peak for this proton, and the compound of interest peaks will be very much low in intensity. So, you are not going to figure it out that what is happening or which peak is which for the compound, because the solvent peak is the only peak which you are able to see because it is very much intensified. Okay. So, for the CCl4, here there is no hydrogen that would resonate or that would introduce in the NMR. Okay, and here also there is CdCl3. It is the deuterated form of the chloroform. So, here also you are not going to interfere in the NMR because it is not going to give you a proton signal for the NMR. But yes, it is not the particular thing that it is always in the deuterated solvents, or the deuterated solvent doesn't present the protons. It also has protons. See, what happens here is there is a deuterated deuterium exchange between the CHCl3 and deuterium. So it is not that if the deuterated solvent is there that you don't have a peak in the 1H NMR. You have a peak in 1H NMR, but that peak is because of the CHCl3 here in this case of the CDCl3, because deuterium is exchanged with a single proton. So that is why a single proton is going to give you NMR peak, but the intensity would be very much low. Why? Because you are not using absolute chloroform. You are not using that. You are instead using a deuterated form of the chloroform. So in the deuterated form, if it is the 99%, then 1% there is would be the CHCl3 peak. So it will be very much in low in intensity. Okay, so that is why we are using the deuterated solvents, not the pure solvents. Okay, so which of the following solvent cannot be used in NMR? So now what you think, that which solvent is not suitable for the NMR? Any guesses? See, we generally use the deuterated solvents, right? For recording the NMR. So A is the deuterated solvent. Yes, it is. CCl4 doesn't have a proton, so it will not going to show up in NMR, right? Okay. Now CDCl3 is also deuterated. Okay. So it is not going to give you an intense peak in the 1H NMR. So which is left? This chloroform. This has an additional proton which will interfere in the NMR, and it will going to get you a very intense peak in the 1H NMR. So now tell me which is the solvent which will be interfering in the NMR and which will be diminishing your compound signals than the solvent. Just tell me if you have got the point. Sorry? Guys, if you don't know the exact answer, it is okay. Just make a guess. At least you try, na? So if no one knows, so anyone wants to say something? Okay. See, all are the deuterated solvents instead of this chloroform. So this is the correct answer, because the solvent which we cannot use is the uh, solvent which is something else than the deuterated solvents. So all of these three, two are the deuterated solvents, and this doesn't have a proton to interfere. But this proton will show up in the 1H NMR and will intensify the peak very much than the compound peak, and that is why you are going to see the 1H NMR peak of this particular solvent in very high intensity, then the compound of interest. So your peaks for the compound of interest will diminish, then the solvent peak, which you doesn't want. Okay, that is why we are using the deuterated solvent to diminish the large solvent signal and to increase the intensity of the compound. Okay, so I hope this problem is clear to all of you. If not, just let me know in the next lecture. Okay, so I'm coming to problem 8. Equivalent protons in a molecule will have equivalent protons. We have talked about the equivalence. See, what happens here is, first of all, in benzene ring, all the protons here in the benzene rings are sp2 hybridized, are equivalent in nature because they have the same chemical environment around each other, right? So these are the same set of protons that are present. So now this, if the question is saying if the equivalent proton is there in the molecule, what will have? That a same environment, a same chemical shift, same shielding effect, or all of the above. So what will happen here? See, what happens here is, if the equivalent protons in a molecule is present, then they will have a same environment as that of the proton that are present in the benzene ring. See, have the same chemical shift because there is no substituent that would affect the chemical shift of these protons. So these chemical shift of these all the six protons will be same for all of the six because all of the six have same environment. That is why they have same chemical shift, have the same shielding effect. So the equivalent protons, if present in a molecule like this in the one this heptane system, sorry, this pentane system, sorry. So if we have this pentane system, then also we have these methylene groups which are equivalent because we have no substituent like Cl or something else that is attached to this particular CH2 or something else, which will again convert or changes the chemical shift value by the shielding or de-shielding effect. So there is no de-shielding or shielding effect which is present in this particular system because all the protons here are equivalent, all the protons have same environment, all the protons have the same chemical shift value, and there is no group that is present to just de-shield or shield the group. Okay, so if a system have the equivalent protons, then it would have a same environment, same chemical shift, same shielding effect. So the correct answer will be all of the above because equivalent proton as that of the benzene ring have the same chemical shift value, same environment, as this H is surrounded by these protons, this hydrogen is surrounded by these protons, these hydrogen is also surrounded by protons. So all the environment of these protons of the benzene rings are same. So they have the same chemical shift, they have the same shielding effect. Is it clear? Guys, just respond so that I can know that you guys are getting
Yes,
something.
yes, ma'am, yes, ma'am.
Okay, okay. Thank you for responding. So the protons for this particular benzene rings are equivalent. So if we have a same equivalent protons in a molecule, then all the above scenarios are same. That the same environment, same chemical shift, and same shielding effect will be there. Okay. So this is the chemical shift ranges which I have just mentioned for you guys. Just have a look on that so that you can have an idea that what is the things which are present at the chemical shift values. Okay. So how the shielding and de-shielding will play a role to suppress the chemical shift value of protons. So coming to the problem 9, how many number of peak splittings will be observed for secondary proton in a following compound? See, they are asking the number of peaks. Anyone wants to say something?
Ma'am, answer for this question is three, ma'am. Option A.
Don't be too fast. Just listen to the question carefully and then you will get to know. See, if you are saying that the different number of signals which are present, it is very much clear that it is 3. It is the correct answer. But here it is not mentioning that number of signals. They are asking that how many number of peak splitting will be observed for secondary proton. See, number of peak splittings. Now you are going to have some splittings in the NMR, not the number of signals. Okay, if you are asking about the number of signals, then your answer is right. That is three. But how many number of peak splitting will be there? See, now you have to calculate the splitting. See, I have just expanded the thing. Here, for the methyl, as for the splitting, we use the n plus 1 rule. Right? For splitting, this is the universal rule. So, for methyl group, if it is present in the vicinity of these hydrogens, then it is 2. So, 2 plus 1 will be the triplet, 3. So, for methyl, we are going to have a triplet because of the protons, that is 2 on the adjacent carbon. Okay. So, if you talked about this CH2, then it is surrounded by this two protons. So, now these two protons will split the signal for this proton, which is this, right? If we mark it as A, B, C, then it would be good. So this is A, this is B, and this is C. Okay. So for CH2, which is C, the proton C will have a splitted pattern because of the proton B in the NMR. So now for calculating the multiplicity for the HC, it is going to have, now the number of protons is 2. So 2 plus 1 will be triplet. Again, it will going to give you a triplet. Okay. But for this, it is very interesting. So just have a look on this. For HB protons, it has both these HA protons and HC protons, which are present in the vicinity of this particular HB protons, right? So HB protons, if it is going to get a single signal in the NMR, then because of the CH3 protons, that is the HA protons, it is further split into a quartet because there are number of hydrogen is 3 and we have the rule 3 plus 1, that is a 4, which is a quartet. So now it Ha proton is splitting the Hb protons into a quartet. So again, now this quartet is not the thing which in NMR you will see, because now there are all Hc protons also which are present in the vicinity of Hb protons. So the Hb protons will going to have a splitting because of Ha proton and Hc protons. So both protons will be playing a role. Okay. So for the Hc proton, there are two protons. So 2 plus 1, 3. That is a triplet. So there are two splitting that would be observed in the case of Hb protons. So quartet plus triplet will give you a septet. Will give you a septet. That is 7 signals. And 4 plus 3 is 7, right? But what happens here is one signal less is shown in NMR. So if you have something like this in the system, if it is splitted by two set of protons, both on the right and the left. So what happens here is quartet plus triplet, that is septet. But in the NMR, you are going to have a sextet for this CH2. That means that this Hp proton will be showing up as a sextet in NMR, not as the septet. Okay, one signal less is shown by the HB. So this is the kind of thing which is happen in this system, in which where there are both hydrogens present on both the sides. There are hydrogen on both the sides. That is why HB is splitted by both HA and HC protons, right? So the signal which HB shows here is the sextet. That is 6. Okay, that is a sextet. Is it clear?
Yes, ma'am. And
Yeah.
I'm sorry, ma'am, for the wrong answer and the
No, no,
first.
it's okay. It's perfectly fine because you have tried and your answer was right in the different sense, because you are thinking that it is about the number of signals. If it is about the number of signals, then your answer is perfectly right. So for the first class now, you are doing very well. So see what happens here is you are getting a sextet, and for this you have a triplet, and for this also you have a triplet. So the question is asking that how many number of peak splitting will be there. So number of peak splitting, right? So splitting we have calculated. So total number of splitting will be like 3 plus 3 plus 6. So that will be 12. So the correct option will be D. How it is coming as 12? See what happens. The number of peak splitting will be 1. You are getting a triplet, that is 3. A sextet, that is 6. And a triplet again for Hc proton, that is 3. So 3 plus 3 plus 6 will get you an answer of 12. So the correct answer will be 12. I hope it is clear. Okay, so
Yes.
I'm going to the last problem of this session, that is problem 10. So which of the following has a more chemical shift? See, amongst this you have to calculate the chemical shift value. So what happens here is due to the electronegativity. See what is here? The halogens, fluorine, chlorine, bromine, iodine. The substitution is different on all the methyl groups. So this is the difference, particular difference between these four options. So we have to figure out which is having the more chemical shift. More chemical shift means which is the more downshield, which is the more downshield proton. Okay, because in that case we have seen now that this delta ppm value we have seen, right? So they are asking that which of the following have more chemical shift. More chemical shift means that as we are going on the left hand side, the chemical shift value is increasing, so we are going to have a downshield proton. Okay, so now we have to look at which of the among is the most downshielded proton. So due to the electronegativity, we are going to answer this particular question. Now, we know that fluorine is more electronegative than chlorine, then bromine, and then iodine, right? So, going from the electronegativity point of view, if something is connected to a very electronegative atom, what is electronegativity? That the basically a tendency of an atom to attract the shared pair of electron towards itself, right? So fluorine has a very high electronegativity, as we know. So if it pull outs all the electron density towards itself, then this carbon is becomes the de-shielded, or becomes the electron poor. In the same, in the lame words, it is electron. It is not electron rich. It is electron deficient, right? So if this carbon is attached to the fluorine, that is a very electronegative atom, it just suppress the electron density at this carbon because it is attracting the electron density towards itself, right? So now this carbon will become the electron deficient carbon, and this hydrogen which will become the electron deficient hydrogen. So now if there is no electron density to oppose the applied magnetic field is in direction. So if this hydrogen doesn't have an electron density on this carbon to oppose the applied magnetic field by making the secondary magnetic field, then what happens what happens is that this applied magnetic field is the only field which is experienced by this proton. So it is very high, and now we have talked that now it will resonate at a higher frequency, right? If the shielding effect is high, then we are supposed to get a lower frequency nuclei. But if the shielding effect is not there, see, shielding effect is very much little because here there is no electron density which is present on the carbon. So how it is going to produce a secondary magnetic field, and then it is opposing the applied magnetic field, right? So there is very little secondary magnetic field which is getting generated in this case. So that is why it is not opposing the applied magnetic field completely. And now the applied magnetic field is the only magnetic field which is experienced by this proton. So it is very high. That is why the proton will become de-shield. that is electron deficient. It is electron deficient, that is why it is resonating at a higher resonance frequency. Okay, so according to the electronegativity only we can answer this, that if a compound has higher electronegativity substituent that is connected to the carbon or the hydrogens, then it is going to have a high chemical shift value, uh, because it is going to have a de-shielded region, right? Because fluorine is abstracting all the electron density, so there is no thing to produce the secondary magnetic field which is opposing the applied magnetic field. So the nuclei is experiencing only the applied magnetic field. So applied magnetic field is very high, and now the hydrogen will resonate at a higher frequency, high resonance frequency. So if it is resonating at a high resonance frequency, then what happens is that it will have a high chemical shift value. We have talked about this, right? So is it clear, the electronegativity trend? Okay, so if it is clear, then you can surely understand that which compound has a more chemical shift. So, more chemical shift means that it is resonating at a higher resonance frequency. So, fluorine, as we know, is the most electronegative atom here. So, it is the CH3F compound protons which are resonating at a higher frequency, because bromine is not that much electronegative to attract all the electron density toward itself. So carbon has some electron density, so it will be producing some secondary induced magnetic field, so which is opposing the applied magnetic field. So the resonance frequency of this proton, when we compared with this proton, is high, is low, sorry. So this proton is resonating at a lower resonance frequency when we are comparing about this proton. Okay, is it clear?
Yeah, ma'am.
Okay, so the correct option will be,
The first option, ma'am.
yeah, the first option will be the correct option, because due to electronegativity, it is suppressing all the electron density at this particular carbon, and it is not able to produce as much effective secondary magnetic field to oppose the applied magnetic field, due to which this hydrogen is now resonating at a higher resonance frequency. And if it is resonating at a higher resonance frequency, it is clear known that high chemical shift value is known for this particular proton. Okay, so the chemical shift value I have mentioned here is very much high for methyl chloride. Okay, so the fluoromethane have a very high resonance frequency and a very high chemical shift value. So I hope this explanation is clear to all of you, and I'm just going to end this session now with this problem. And if you have any problem with the solution which I have given today, just let me know in the next lecture, and I will surely answer you again. Okay. So thank you for joining, guys. I will be taking the sessions at Sunday 3 to 4. So just connect timely. Okay, it is very irritating to connect someone in the middle of the lecture. So please be there at 3, and thank you so much for listening me patiently. Thank you so much.